Notice I've changed nothing about states. I've said nothing about function approximation over states. I'm talking about abstraction over this set of actions that you have.
Well, you did implicitly talk a little bit about states when you said that all the states in, say, the northeast room end up being sort of equivalent.
Right. Equivalent with respect to the action that you want to take, yes.
Yeah.
Right. Which is its own kind of approximation, its own kind of abstraction. All of these are different kinds of abstraction, really.
Okay.
And will allow us to do scale. So let me just add one more thing to this before we move on to the next slide. And what I want to point out is that this isn't just a way for you to think about this problem or to sort of in a compact and efficient way explain how you would accomplish a particular goal. It actually has other computational benefits. So if we think in this sort of southeast room here about how value propagation works, right? You took a bunch of actions in here, you got to this good space, then you start backing up values, right? So I know this is worth a lot because 1 is the biggest number in the universe without loss of generality. Assume 1 is the largest number. And then I'm going to learn that being in this state and taking this particular action is also good. I'll just draw a little dot here, the big size saying that's really good, and a slightly smaller dot and a slightly smaller dot. And so the value of the states around here are nice and big because I can easily get from here to the goal state. And as I move farther away, the value gets to be, a little bit less, and then a little bit less, and a little bit less, and it sort of propagates out into the other rooms. And the way that you propagate this information is actually kind of slow, right? You have to get to the state and sort of back it up a little bit. Your horizon is such that the value seems relatively small, and you kind of keep going. And you have to visit this often, very often actually, to back up the information to tell you sort of what the value of the states are, what the Q values of state and action pairs are. And that's fine. That's how we do that's how we learn in MDPs. But because I have this abstract action, I have this go to doorway, I can actually, from here, from this particular state at the doorway, back up information all the way to here, wherever it is I executed that particular action, in sort of one step. So I learn a lot about the value of being in this state immediately from having taken that and gotten here. So as soon as information from my little +1 box here gets me to here, I can back that information all the way up to where I initially executed the go to doorway X. And similarly, now that I've got information here, I can back it all the way up to the value of being in this state. And so I can back up information and value much more quickly without having to back it up sort of one little state at a time. So there's a lot of advantages here, sort of computational and otherwise, that will hopefully allow us to learn faster.
Cool. And I think that's helping me understand why it's temporal abstraction, right? So state abstraction is treating a whole bunch of states sort of equivalently. This is actually treating a whole bunch of time steps equivalently, right? That we can just kind of elide over them.
Right. And now you'll notice that it will have this side effect of allowing us to treat a bunch of states similarly, because we know that for one way of thinking about similarity between states is sort of how their features are similar to one another. That's what you talked about. Another way to think about similarity among states is to think about whether you should take the same action when you're in them. And so every single state in this room is the same in the sense that the optimal action is the same. Go to this doorway.